Hello everybody. In this class, we shall look at use of shift register in serial addition, multiplication and division. Okay. That means in arithmetic circuit building. We have seen them this addition, multiplication and division in combinatorial logic related discussion, and there we told that there are other ways, other way to do it, and one is using sequential logic based implementation. So, we shall see how it can be done using shift register. Okay. So, we begin with serial addition. So, in serial addition what we have is this shift register, two shift register we are putting. One is your register A and register B. So, in this the addend and augend they are put, okay. And when you are clocking it, then this is going serially out, coming serially out, and the way it is put, the most significant bit is this side and the least significant bit is the other side. So, this here. So, if it is A7, then this is A0. So, this is the LSB, okay, and this is the MSB. Similarly, this is B7 and this is B0. Okay. So, this is the way initially it is put, right. What else? So, instead of if we are talking about 8-bit addition in combinatorial logic context, we have seen that 8 adder units are required. Here we are using only one adder unit, the one that you see here, right, and we are using it successively. In every clock cycle, it is doing a 1-bit addition, right, and the carry output of 8 that is generated here is stored in a D flip flop, okay, and this is fed back here for use it in the next bit addition, okay. And the sum bit that is getting generated, that is coming as serial in and is stored in register A. What happens to steady register B? The serial in that is there, we can put another number. So, if you are looking for consecutive addition of A plus B plus C plus D, okay, more than 2 numbers. So, we can make C enter at that time through this particular serial in, okay. So, after 8 clock pulses, what will happen? That A plus B result will be stored here, okay, with carry, and then by that time C is already loaded here. So, with another 8 clock pulse, A plus B plus C will be generated, okay. So, this is the way it will go on. Is it clear? So, we can see one example. For example, we have 2 numbers, say 140, 1010. So, this is A and this is B initially loaded and Q is 0, okay. And when after 1 clock pulse, what will happen? So, 1 and 0 it is getting added. So, that is 1, right. So, this 1 will be after 1 clock pulse, because it is fed back here, it will come over here, right. Since carry generated is 0, 1 0, it is, there is no carry. So, Q will be 0 only. So, 0 will be coming here, right. And for B, after 1 clock pulse, the next number or some other value, which is of no significance will come here. So, if it is the next number, or if it is 0, 0 it will be there, or 1 it will be 1, okay. Otherwise, we say it is we do not care. So, next clock pulse, what will happen? Within this, because it is a combinatorial logic, 1 plus 1, which is 0, is generated and carry generated as 1. So, this is 0 and carry generated as 1 within the same clock cycle, but we need the clock trigger for this 0 to come over here. So, next clock trigger, so this 0 that is generated will come over here, this 1 will get pushed, right, everything will get pushed, 1 0 is coming over here, okay. Now, this carry which was at this input with the trigger will come over here and it is there, okay. And for B, another such input will come, okay. So, this way it will keep doing it, and after 8 clock pulses the addition will be completed. Is it fine? And here you can see the snapshot of it. So, A7 to A2 after 2 clock pulses where it is. So, B7 to B2 is here. So, these are A2, B2 and C1, that is the carry of the previous clock as previous addition, previous bit number 1, A1 and B1 addition is over here, okay, and S2 is entering with the clock, next clock, clock 3, S2 will enter here, okay, and these 2 places, the next number or some junk value, or we do not care which value are entering in this particular place, okay, right. So, earlier we are doing it at one go, here we require 8 clock cycles to complete the addition. So, this is the difference between parallel addition using combinatorial logic and serial addition using sequential logic. Okay. So, there it was faster, but requiring more hardware, here it is slower, it requires more time, okay. But it is, if it is the clocking is sufficiently fast, then you know, it can be done in real time. Okay. So, next we look at serial multiplication. Okay. In serial multiplication, what we are having, first let us get familiarized with the hardware that we are using. Okay. So, the 2 factors to generate the product. So, one is x3, x2, x1 and x0, right, and the other one is y3, y2, y1 and y0, right. And in addition to that, we are using a 7-bit adder. Note that it is a 7-bit adder and a register which is 8-bit long. So, we are giving an example of 4-bit and 4-bit multiplication, right. So, it can be extended for other cases. So, this is a latch, right, this is a shift register, the arrow direction shows that gradually it will be shifted. Okay. So, first we will you know, multiply with y3, we will get the partial product which will get added, then again we will multiply with y2, and this AND gate outputs will be giving you the bitwise multiplication, y2 multiplying these x3 to x0. So, we shall see one example, of course, right. And the other important point to be noted here, of course, the M initially is loaded with 0, 0, 0, 0, okay, is that the M0 to M6, these values after addition is coming here as M1 to M7. Please note this part. Okay. So, inherently in the structure, we are having a one left shift occurring. The arrangement is such that the wiring is such that a left shift is occurring when we are loading the addition result. Okay. Now, this 7-bit addition for which 7 bits are taken from here, and this AND bank, the first is not required. We shall see an example, okay, why it is not required. So, this 3 AND output will be going to the adder, and for the rest of the cases we will be having zeros. Okay. So, that both sides we are having 7-bit. Okay. Is it fine? So, this is the hardware part of it, and these shifting and loading are not happening in the same clock edge. So, when shifting is happening, not that at that time loading is happening. Okay. So, when shift happens say at the negative edge, right, after that this combinatorial circuit does its operation with whatever propagation delay is required, result is available. Okay. Next positive edge, it gets loaded. So, that if the whole thing gets completed in one clock cycle itself, okay, but it is in this manner. Okay. And the example that we shall take is the one which we have seen before, that is 1101, okay, in our combinatorial logic circuit discussion for multiplier, and we saw that this was the result. Okay. and the corresponding decimal value was 143, right. So, we shall see that example in the next slide. Okay. So, the circuit in a bit smaller form, we have placed it here for easier understanding, and we start with this x3, x2, x1 and x0, it is always there 1 1 0 1, okay, and y3, y2, these will be coming getting shifted over here. So, first the y3 will be considered. So, y3 ended with 1 1 0 1. So, the AND output over here, what will be those values? 1 1 0 1 only. Is it okay? This AND output is 1 1 0 1. Okay, it's clear. M output initially is all zeros, right, and out of these all zeros, 8 bits, this one in the blue, the 7 1, okay. So, that are getting fed back as the adder input, okay. So, this is this 7 will be there, right, and other adder input is what? This one is not used, this is coming directly as per the circuit diagram, you can see, to the M0, okay, and the rest 3, that means 1 1 0, okay. So, this 1 1 0 and rest 4 are 0, rest 4 are 0, rest 4 are 0, and this is 1 1 0. That is these 7 bits for are going as A and B for the adder. Is it clear? Right. So, what is the result? So, this one is coming directly as 1, right, and the other cases. So, this is 0, this is 1 and this is 1 and rest are 0. And after the clock trigger, what is happening? What is getting fed here? What is getting loaded here? So, this M0, this 1 is getting directly loaded here, and the adder output will be coming at M1 to M7. So, 0 0 0 0 1 1 0. Is it fine? Understood? Right? So, now this is the value of M, right? This is the value of M. It is getting shifted negative edge. So, it is becoming, what is the output for the AND gate? All 0, right? M output is now here, whatever is the output next clock cycle in the beginning, this is the output of the M, and which of that is going as adder input? The M0 to M6, M0 to M6, right. So, this is going as adder input in the blue, right, and to which what is getting added? These 3 bits. So, these are all zeros in this case and rest are all 0, and this 0 is directly coming. So, what will be the corresponding addition result? This is the addition result, okay. So, what effectively you see that it is just getting shifted when you are multiplying with 1 0. In this particular case, it is just getting, the first one is getting multiplied properly, and then it is just getting shifted by for the case of the 0 by 1 unit, okay. So, that is the inherent shifting that is happening. We are not doing any shift register based shifting, it is not required, okay, and we are saving on clock cycles, and also the complexity of the circuit is reduced, okay. So, after that what we are getting, the value of this shift register becomes 0 0 0, this M register becomes 0 0 0 1 1 0 1 0, okay. So, 0 0 0 1 1 0 1 0, and now again it is getting shifted. So, this 1 will come, y1 will come. So, what is the AND gate output? 1 1 0 1, okay, and out of that this 1 will come directly, and 1 1 0, 1 1 0 appended with 4 zeros is the 7 bit adder B input, and for the A input, this M0 to M6 is coming here, M0 to M6. Then if you add, this is 1, then 1 plus 1 is 0, 1 plus that carry is 1, 0, carry is 1, 0, carry is 1, 0, and then we have got a 1. So, this is your M register, okay, which is which will be taking the value after clock 3, right. So, this will be now coming here in the next clock cycle, and this is the input, the 6 M0 to M6, 7 bits will go as adder input, okay, right. And here again Y0 is 1, so this is 1101, right. This 1 is coming directly over here, and 110 and 4 zeros, that is participating in the addition. So, what we get, this is 1, this is 1, this is 1 and this is 1, and these 3 zeros and 1. So, the after clock trigger, this is the adder output, this is the value that we get. Okay. So, this one is 128 and these 4 ones 15, 143. Okay. So, this is the way we can see that we can through this partial product and shift we can get the multiplication done. So, this is the same example we had seen before, you can compare the result, okay, and you can perform it by hand also. Now, we shall look at division. So, for the division we shall just implement the circuit that we had used for combinatorial logic circuit, its sequential version. Okay. So, for which I have brought that particular unit cell based architecture, the array we had used. Okay. So, if you remember, fine, otherwise please revisit that particular lecture. I believe it is lecture number 30. Okay. So, week 6 last lecture, then it will be clearer to you how this division takes place. So, we have taken up this example which is there in the right hand side. Okay. So, the same example you can see in that particular lecture module also. Okay. So, the this is the dividend, this is the divisor, this is the quotient, and this is the remainder. Okay. And we had seen how it actually getting calculated through this, and how we can arrive at these numbers. Okay. So, this dividend D6, D5, D4, D3, these bits are taken first, right, and then gradually D2, D1, D0 are added. Added means it comes into the consideration. Okay. This is important because in the next circuit, sequential logic based circuit, we also see that initially D6, D5, D4, D3 are there, okay, these 4 bits. So, then D2, D1, D0 are there. So, this is a 7 bit getting divided by 4 bit, this is a specific example. So, you can extend it for 8 bit and other cases. Okay. And in every case, see this D3, D2, D1 and D0, okay, that is participating in the subtraction process. Okay. Either the subtraction result is going to the output, or this X is going to the output because of the multiplexing 2-to-1 multiplexer it is there. So, it is the borrow out which is deciding it, and borrow out inverted is the quotient that is getting generated, and finally, the remainder will come over here. Is it okay? And these are the quotients, and this quotient is also available here at this side. So, here also you get this quotient, in the right hand side also you get the quotient. We had in that example we had taken it from the left hand side, but we could have taken from this output also. Okay. Is it fine? Right. So, this is what we had done in that particular class. Okay. So, now we see how it is getting implemented there. So, D6, D5, D4, D3 we shall begin with, then D2, D1, D0 will get appended sequentially, right, and every time D3, D2, D1, D0 will be in consideration. Q3, Q2, Q1, Q0 will be generated through the borrow, and finally, the remainder will be there. Okay. So, this is the thing that we take note of. Okay. And this is how the serial division takes place. Okay. So, first of all, you can see this D0 to D6 that was there. In addition, there is another bit we have put. So, it is 8 bit register, okay. So out of this 8-bit, I mean basically we are dividing into a 4-bit register, parallel in parallel output kind, another is a 4-bit shift register. So D0 to D3 is a 4-bit shift register, okay, and this one is a parallel in parallel out register, okay, and this is just a latch or a parallel out register which could be serially in, parallel in, depending on the requirement. Once it is loaded, it is not, I mean the output is always being used, okay. Is it fine? Right? And these are the unit cell, one bank of it is only required because it is sequentially used, right. So, how it works, how it implements the one that we had seen, the circuit, the combinatorial circuit based circuit. So, here we are in this particular case. So, in the beginning D6, D5, D4, D3, you see this is the output, this is taken from here, right, and D7 is also there. Okay. First of all, in the beginning D7 is not of consequence. So, D6, D5, D4, D3, that is being used, right, and it goes through that particular block, and whatever is the generated, this Q, this output, it is also generated through here. So, this is made available. This is a combinatorial logic block, isn't it? Now, with the clock, what happens? This quotient Q0 comes over here, right, and D2 takes place of D3, right, and now this D6, D5, D4, and I mean what is the the particular value that comes over here from the unit cell, either this one or the subtraction value as per the logic, okay, that will be there. With that D3, the D2 also comes into consideration. So, these three values 1, 2, 3, okay, and D2 comes into consideration, and in each case D3, D2, D1, D0 is there. Next time again this will be coming into consideration, okay, and D1 also comes into picture. So, this is how it progresses. The same thing is implemented in the same manner. The example that we had seen, you can just put over here, and with the clock you can see it moves from exactly the same manner, and the same result will be found at the end, okay, right. And as we had mentioned in the previous case, here also this 1 and 5 could use half subtractor instead of full subtractor. Again I say that we are following the division paradigm that we had used in the combinatorial logic circuit based divider circuit discussion. So, please refer to that and then come back here, it will be easier for you to follow. Okay. So, with this we come to the conclusion of this particular class. So, what you have seen, serial addition uses an adder circuit, adder unit successively, where consecutive bits are presented from shift register, and the carry part of it can be handled by a D flip flop. In serial multiplier realization, one of the factors is shifted through a shift register and one bank of AND gates, and the adder block is used successively. In storage of adder result, one left shift is made. So, the storage part is made in such a manner, intelligent manner, that we do not require in any separate shifting that we see in the multiplication process. Okay. So, in serial divider realization, the one that we have seen, we have a unit cell based approach where one bank of unit cell comprising of subtractor and multiplexer is used in a successive manner. Okay. And these unit cells in the divider circuit receive the dividend bits through a register, and a shift register where shift register introduces the lower 4 bits, and the remainders are stored in the higher bits, that is D7 to D7, D6, D5, D4, the way you have seen, and D3 to D1, D3 to D0 now is the placeholder for the quotient. Okay. So, with this we conclude the discussion on shift register. Thank you.